Okay, so before I do anything, I want to make clear a important um, consequence of linearity of integration for simple functions. In particular, um, let's say I have a simple function on E that's non-negative. And let's say I can write it now. I can write, let's say I write it in any way I want as a linear combination of characteristic functions where all of these sets are a subset of E and each of the yi's are bigger or equal to 0. I don't really care if the EI's partition E. I don't care if this is the canonical decomposition of my simple function. So as long as I have this here, and the EIs we're assuming are measurable. So if as long as the EIs are measurable, then from what we proved before, in particular, integration when dealing with simple functions is linear. Certainly these are simple functions. Obviously, each one of these here is itself a simple function. So we can just integrate each term in the sum, pull out constants. So we get this fact regardless of whether this is a canonical decomposition of my simple function var phi, and regardless of whether the EI's partition E. Here we're just assuming the yi's, as they have to be, are non-negative, and the EI's are a subset of E, and they're measurable. Okay? So just something to keep in the back of your mind. We'll go back to this later when we prove that integration is linear for general non-negative measurable functions, not just simple functions. Okay, anyway, so first, after that, let's get something out of the way. So for a simple function, we have seemingly two different definitions. So what do I mean by that? So actually, give me 1 second. Right, so we had this definition of a simple function, the definition, okay, where this is the canonical decomposition of my simple function. Though, as I just proved, it really doesn't have to be. If you know, you can write it really in any way you want as a linear combination of characteristic functions and integrate as you kind of would expect you should be able to integrate. But we also have this definition for a more general measurable function. So in particular, just changing notation a bit, according to the second definition, if this is a simple function, we can write this in the following way. So I'm not going to use var phi. I'll use, let's say, var phi tilde. Lack of anything better to call it. Okay. So yeah, we have these two basically definitions here. And let's prove that they're going to be equal. Okay. Let's prove that they are going to be equal. Okay. So I'll call this definition star here and this definition star star. All right. And this is not going to be hard. It's a little annoying, but So yeah, we have a proposition for a simple function. And I'll try to be efficient with notation. There's just a lot of sets to write. It's annoying, but that's his life. So we have these two are equal. Okay. So this here is star, and this here is star star. Let me get rid of this. Not that it matters all that much, but okay. So one direction is absolutely, almost absolutely trivial. Okay, so yeah, that. Okay, so this is simple. So in particular, that means this is going to be in the following set, just absolutely trivially, by setting var phi tilde to be just var phi. Right, and so just trivial, definition of supremum, really. So this integral here, sorry, what I meant was this integral is in here. Again, just setting var phi tilde to be var phi. So this integral here is less than or equal to star star here. Simply because, well, star star here is the soup of all these integrals. This is the soup of all of these integrals. Okay. And to be clear, when I haven't had it written, but to be clear, when I write the soup of these integrals, I mean the original definition of integrating a simple non-negative function. Okay, and yeah, of course, when I write this, I mean this here is star. Okay, so now all we have to do is prove the converse. And we're going to prove it looking at two cases. That's going to be the easiest thing to do, is look at two different cases. So the first case is going to be if this supremum is finite versus infinite. So let's say this is infinite. So I want, and I'm going to stop saying simple because it's just annoying to write. It's more annoying to fit it in. But so whenever I write this, I mean this is going to be simple. That's okay. So this is the supremum is infinite. Then that means this set here is unbounded. So for any natural number n, what do we do? Well, pick simple var phi tilde on E, where this is bigger or equal to n. Okay, but integration against simple function is monotone in the sense that it preserves inequalities. So this is true, and that's going to imply this is true, what I'm about to write. Remember, we haven't proved it yet for general non-negative measurable functions, but these are two simple functions, so we have proved that. This is bigger or equal to n. So leave it. Yeah, so that means this has to be infinity because this is for all natural numbers n. We just picked an arbitrary natural number n, and we proved the integral of E, integral of r phi over E is bigger or equal to that n, so that means this has to be infinity. So this is star here, and this is star star here. So they're both infinity. Certainly infinity is less than or equal to infinity. Okay. On the other hand, if this is finite, we can assume that the set is bounded. Right. So on the other hand, if this set here is bounded, let's find a little yellow here. All right, so it's just a little easy epsilon. Oops, no, do that. Little easy epsilon stuff. So pick epsilon bigger than 0. Okay, so I'm going to pick simple non-negative var phi tilde less than or equal to var phi, where this is true. Just definition of supremum, basically. I'll explain it in a minute. Yeah. This is really annoying me, so let me get rid of that. Okay, so right, supremum is the least upper bound. Subtract epsilon, that's no longer a upper bound, so I can always pick a var phi tilde where this is true. Or really, I should probably do var phi tilde tilde or something else. Yeah, maybe rather than that, I'll use psi here. Yeah, let me do that. Basically, I'm saying the sup minus epsilon is not an upper bound. So I can always pick one of these integrals where this is true. Okay, but again, this is less than or equal to phi. So this is going to be integration preserves inequalities in this way. So, right. So be clear, this is definition of soup. And this is from this here. And of course, this is on E. Okay, yeah, and that's, we're done because this here is star, this is star star, and it's epsilon. That's exactly what we need to prove. This is true for any epsilon whatsoever, so really easy proof. Um, yeah. So to be sure, um, so yeah, we proved star is less than or equal to star star, and here we proved star star is less than or equal to star. So no issues. Yeah, so no issues. These two definitions are going to be the same. Yeah, so there's no ambiguity on which definition I mean. They're both the same as long as we're dealing with non-negative simple function. Okay, so yeah, let me prove some more basic results about integrating non-negative measurable non-negative measurable functions in general. These are annoying to prove, but basically once we finish the proof of these, we'll rid ourselves from annoying proofs. I would say this is the last annoying proof video we're gonna do. The rest is gonna either be kind of a more deep proof or using kind of the big guns, Fatou's lemma, dominant convergence theorem, monotone convergence theorem. But right, okay, so yeah, so let's say in general, E is measurable, F is measurable. Okay, so we have three properties. One, alpha is bigger or equal to 0, then I can at least pull out constants. So after this, we'll get to a deep result that's easy to prove, Chebyshev's inequality. Yeah, very useful result. So as I mentioned before, I'm not going to prove additivity of the integral in general. It's much easier just to prove, particularly prove the monotone convergence theorem, and then use basically use a monotone convergence theorem to prove that integration is additive in general. That's just a much more efficient way of doing things. And I don't know of an I mean, you could just use this definition here to prove additivity, but it's a pain, and why bother? Let's be efficient here. Okay, two. Says I can always excise a set of measure 0 from integration. So this is something you'll use over and over and over and over and over again, and then use it some more. Okay, and last but not least, and I'll try to go as quick as I can for these proofs. So if this is also measurable, E, sorry, you don't need on E. You need almost everywhere on E. So the set where it's false has measure 0. Remember, AE means almost everywhere. Right? So that's convenience. Okay. Let's get another page here. Okay. Yeah, so let's prove this. So that. Annoying. Yeah, that. All right, so proof of one. How do we prove one? All right, so yeah, this is pretty easy. So first, so 0 times infinity, as I mentioned, we define as 0. I can assume that loss of generality that alpha is positive. Why? Because if alpha is 0, then both of these here are going to be 0. This will be 0, this will be 0. In particular, integrating the 0 function by definition gives you 0. If you have any doubts, go back to definition literally right here. On the other hand, if the integral is infinite, then 0 times infinity still gives you 0. So if alpha is 0, both of these are 0. So assume alpha is positive. Okay, so if alpha is bigger than 0, I'm just going to use the definition of this integral here. Okay. So the definition, well, just instead of var phi, just plug in f. So or sorry, plug in alpha f. Plug in alpha f. Right. So alpha f, alpha f. Okay, so it's going to be the supremum here. Okay, so what I'm going to do next is, and I can do this because alpha is positive, I'm going to divide both sides by alpha here. And then multiply and divide by alpha. So I'm going to multiply and divide by alpha. But looking at all these integrals, if you think about it, is the same thing. And if you have any doubts, just prove it. Prove that these two sets are equal. And of course, here, this is simple. So for every simple var phi tilde where this is true, we can come up with var phi where this is true and vice versa. Okay. So yeah, what I'm saying is these two sets that I'm putting in a rectangle, these two sets are equal. Okay. Well, now I can pull out this constant here, and that finishes the proof. Because this here is the integral, it's alpha times the integral of f by definition. Okay. Oops, do that. Right, so without the alpha, this is the definition. I don't care what notation I use, tildes, no tildes, whatever. And of course, sorry, this is on E, et cetera, et cetera. All these are on E. Okay, so yeah, easy proof of one. Okay, right, so this here is going to be the following supremum. And the point is we don't care about supremums per se. We're going to prove actual set equalities. Of course, this is simple. Let's do it once. These two, I'll write it. Okay, on the other hand, this by definition, so f technically is not a function on E prime, it is a function on E. So remember how we defined it. This is the definition. It's integral over E, characteristic function E prime. Remember, E prime is a subset of E and is measurable. F. So it's going to be the same thing. Except instead of F, it's the product of these two. Again, this is overall simple functions. All right, so the goal here is to prove that this set equals this set. I'm going to prove that these two sets are equal. And if I do that, obviously the supremums are going to be equal. Okay. Yeah, so if this is true, then trivially this is true. Because what is this saying? On E prime, this is just F. So we have this is true on E prime, but off of E prime, this is saying var phi has to be 0. Okay? So if this is 0, then well, 0 is less than or equal to F. So this is kind of trivial. This is basically trivial. Okay, so this is saying every integral here is one of these integrals here. Let's squeeze this in. Again, looking at all simple functions of var phi here and here. So, yeah, again, take one of these integrals. We'll just use the same var phi, because any var phi here satisfies this condition here. Okay. All right, so yeah, that's half of this. So let's prove the other half. The other half is easy, but a little more. Okay, so let's say S is in this set right here. Again, this is over, these are both over simple functions. So yeah, let's assume this is a simple function. So S, you can write it as this here. Okay. Where this is going to be as follows. So I don't even care if this is the canonical decomposition of var phi, because no matter how I decompose my simple function as a linear combination of characteristic functions, this is always going to be true. So to be clear, I'll squeeze this in. Right. Okay. So what does that mean? Well, we haven't used our assumption yet. Let's finally do that. Hope no one's offended by my lack of use of periods. Yeah. So here, of course, is a simple function on E. So as I've said many times, this is a subset of E. So E, take away E prime is 0. So that implies E I, take away E prime is 0. Right. Because EI is a subset of E. So that means trivially, almost trivially, that the measure of EI is the measure of EI intersect E prime. EI is EI intersect E prime, disjoint union, EI take away E prime, and the latter has measure 0. Okay. So what does this mean? It means if you think about it, we're basically done. Why on earth does that mean we are done? That means S is going to be the following sum. Same thing. Well, this here is going to be the following. So this is simply characteristic function of E prime. I'll explain why in a second. it's not clear. Go down a bit more. Yeah, let me move this over a bit. Right, so why is this true? Let's see if I can make this a little neater. Okay, yeah, so I'm going to take this here and just multiply by the characteristic function of e prime. That's all I am going to do. And I'm going to distribute it. So it's characteristic function of e prime, times characteristic function of ei. Well, when you multiply characteristic functions, it has the effect of taking intersections. So let me swap them. Yeah, so that means S is the integral of psi, because the integral of psi is yi, sum of yi times the measure of ei intersect e. Sorry, this should be prime. So that. Right. So right. Right. Okay. Yeah, so what finally, so we're almost done. So this fairly easily gives me that this is true because they're both 0 off of E prime. And on E prime, well, they're both respectively var phi and f. But this is psi. So what does that mean? That means S and yeah, that means S is going to be in this set. And that takes care of the proof. That finishes it. Or rather, S equals integral of psi, and that is going to be in this set here. Because particularly, well, psi is between 0 and characteristic function e prime f, and S is this integral here. So in other words, what did we do? We picked, well, we're done. We picked arbitrary S in this set, and we proved that it has to be in this set. All right, so the two sets are equal. And therefore we are done. So the conclusion is that this set here equals this set, and hence the supremums are equal. Okay, so what I want to do now is prove 3. So I'm assuming F is less than or equal to G almost everywhere on E. Okay. So let's say E prime is going to be X and E, where F of X is less than or equal to G of X on E. So by definition, this is going to have measure 0 because F is less than or equal to G almost everywhere on E. So that makes no sense here. Put the this is up here. So let's use 2 twice. Yeah, by 2 twice, these two are going to be equal. And these two are going to be equal. Okay, right. So remember what this is. By definition, this is following. And by definition, oops, that makes absolutely no sense at all. Sorry about that. That makes a lot more sense. Okay, so yeah, well, so it's clearly enough to show because of this. So it's enough to show these two integrals are equal. Yeah. Yeah, so use the set defining this. Those are, again, as I said a million times, overall simple functions. Okay, but this is going to be a subset. Let me try and squeeze it in. Yeah, why? Very trivially, if this is true, then that means well, I literally did nothing here. But that means this is true. Why is this true? Well, if we're away from E prime, they're both zero. If we're on E prime is a set of all x where this is true, set of all x and E. Okay. So take an integral in this set. We'll use the same verify. You get an integral here. And so by literally the definition of you know, these two integrals here and here, well, just because this, the supremum of the smaller set is less than or equal to the supremum of the larger sets. So that means integral E E prime F is the supremum here. Do not want to rewrite this whole thing. Whatever. Sorry, second. This paint in the ass. Right, so replace this with G, and that's that. Okay, yeah. All right, so next up, as I mentioned, is next up is Chebyshev's inequality, and we'll get straight to Fatou's lemma. So one thing I do want to I'll leave this as an exercise. Curious, yeah, definitely try this. It's pretty straightforward. So if I have a measurable E, non-negative, A is a subset of E. Let's say F tilde is F restricted to A. So thinking of this as a function from A to infinity, and assume A is measurable. Then this here, so I'm gonna write it like this. So I can actually write it. Yeah, so this is going to be equal to F tilde. Okay. And remember what this definition is. Definition here is characteristic function of A times F. Yeah, so this is a good little exercise to do. It's again, you prove the two sets defining these integrals are equal. All right, so long, take care. Yeah, Chebyshev's inequality and Fatou's lemma to come.